Okay, before we begin, let's go ahead and review the Do Now from Unit 5, Lesson 1. This was the first question we saw. This question says, figure ABCD has been translated 3 units up and 6 units to the left to form figure A prime, B prime, C prime, D prime. Are ABCD and A prime, B prime, C prime, D prime congruent figures? The answer here is yes. They are in fact congruent figures. The reason that we know that these two figures are congruent is because they have undergone a translation. Let us remember that a translation is a type of rigid transformations. And every time a figure undergoes a rigid transformation, it remains congruent. Thus the term rigid. A non-rigid transformation would mean that the figure would change and no longer be congruent. But because translation is a rigid transformation, we can assume automatically that these two figures will be congruent to each other. Let's look at this other problem that we got. This one said triangle CXY and triangle NLM are congruent. What is the measure of angle N? So in this instance, we are directly told that these two triangles are congruent. Therefore, we don't have to determine whether these triangles are congruent or not. Because we know that they are congruent, we know that their angle measures and their side lengths must all be the same. In order for two things to be congruent, two figures, all the angle measures and all the side lengths must also be congruent. They must be exactly the same. That being said, we can reasonably assume that we can transfer this 30-degree angle onto our other triangle where it fits, and this side length onto our other triangle where it fits, thus making the two exactly the same. That being said, if we're being asked to find the measure of angle N, we can see here that angle N is located right here, which is 30 degrees. Therefore, we select 30 as our answer, and we are able to move on. Today we're going to look at two different lessons, both very brief. The first one is Unit 5, Lesson 3, titled Triangle Congruence, SSS and HL. Basically what we're going to look at is two other theorems which can help us prove that two triangles are congruent. Let's go ahead and look at these two different theorems. The first one we can look at is side-side congruence theorem, also known as SSS. This theorem states, if 3 sides of one triangle are congruent to 3 sides of another triangle, then the two triangles must be congruent. So basically in this criteria, or in this theorem, the criteria we must meet is that all 3 sides are congruent. So 3 sides congruent. If we can prove that all 3 sides are congruent, given the information we see here, then we can use the SSS theorem to prove that these two triangles are congruent to each other. So let's see if all 3 sides are congruent in this instance. Here we see we have one line segment which is congruent to another line segment. We have this line segment which is congruent to this line segment. And we have this line segment which is congruent to this line segment, as shown by those symbols located there. Thus, we can see that we have all 3 sides which are congruent to each other from one triangle to the other, thus meeting this criteria. And therefore, we are able to prove that triangle ABC is congruent to triangle DEF using the side-side congruence theorem. Let us look at how we can use the SSS congruence theorem to solve a problem. Here we are asked what value of x would make triangle PQR and STU congruent by using the side-side theorem. The side-side theorem tells us that all 3 of our different line segments must be congruent. So if we're trying to prove it using the side-side theorem, we must determine that all 3 of our sides are congruent to each other. So we see that this one is congruent to this one. And you see here this is 21 units as well as this. So those would be congruent to each other. And thus we're left with our last side, which means that this one is congruent to this one. We're being asked to find what value of x would make these triangles congruent to each other. Well, as you can see here, we are given a bit of information about each side length. we are told that PQ is congruent to TS, where PQ is represented by 3x plus 4 and TS is represented by 13. Therefore, in order to find what value of x would make these two triangles congruent to each other, we need to solve for x using this equation. So let's go ahead and transfer that to equation form. So 3x plus 4 equals 13. And then we'll use our algebraic processes to solve. So minus 4 gives me 3x equals 9. Divide by 3, which gives me x is equal to 3. So therefore, when x is equal to 3, then we know that triangle PQR and STU are congruent to each other because all three of the sides would therefore be congruent to each other. Okay? And the reason we know that is if we substitute 3 into here. So let's do 3. Substitute 3 plus 4. That gives us 9 plus 4. And thus we get 13 equals 13, which means that PQ would be congruent to TS, thus showing us that all three of our sides are congruent. Okay, so let's get into our next theorem, the last theorem we're going to see. And this is the hypothesis-like theorem, also sometimes referred to as the HL theorem. The HL theorem says if the hypothesis and a leg of one right triangle are congruent to the hypothesis and the leg of another right triangle, well then the two triangles are congruent. So the first criteria that we have to meet is that it must be a right triangle. So therefore we must have a right angle or a 90-degree angle. Once we know that we have two right triangles, then we have to just prove that the hypotenuse is congruent and that the leg is congruent. Okay? Once we can prove all those things, we can prove that these two triangles are congruent to each other using the HL theorem. So you may be asking, what is a hypotenuse and what is a leg? Well, whenever we have a right triangle, so I'm going to draw a right triangle here, we have what are known as legs and hypotenuse. The hypotenuse is always the longest side in a right triangle, and it is always located right here. So here we have our hypotenuse. Whatever sides are not our hypotenuse are our legs. So this would be a leg, and this would be a leg in relation to sides. So you have a hypotenuse side and two legs. That being said, if we want to look at our triangles, we can identify the hypotenuse being our longest side. So here's our hypotenuses, and here are our legs. Okay, so let us remember the criteria for proving that two triangles are congruent. So let's see if we can use the HL theorem to prove that these two triangles are congruent. The first criteria we need is that both need to be right triangles. Are both these right triangles? Well, indicated by this box-like symbol, they are both in fact right triangles, so we can check that off. Are the hypotenuses of both triangles congruent to each other? Well, let's see. Here we have this hypotenuse, which is congruent to this hypotenuse, as we can see there by that symbol. So they are, in fact, congruent to each other. And are the corresponding legs congruent to each other? Well, let's see. Here we have this leg, which would be congruent to this leg, indicated by that symbol there. And so, therefore, we can prove that triangle JKL and triangle XYZ are congruent to each other using the hypotenuse leg theorem. Okay. So what did we learn today? We learned about the side-side congruence theorem, which basically told us that our criteria is that if all three sides of our triangles are congruent to each other, well then those two triangles must be congruent to each other. And then we looked at the hypotenuse leg theorem, which told us if we have two right triangles, then the hypotenuse and the leg are congruent to each other, well then those two are congruent to each other. So first criteria is that both of our triangles must be right triangles. The next is that our hypotenuses are congruent to each other. And then the next would be that our legs are congruent to each other. Remember that hypotenuses of right triangles are the legs that have the longest distance and are often located right here, while our legs are our other remaining sides, and thus we would be able to find congruence. Okay. So because that lecture was so short, we're just going to go ahead and jump into our last lesson of this unit, which is also very brief and brings everything that we've learned so far together. So this is basically Unit 5, Lesson 4, and in this lesson we're using triangle congruence theorems to prove that two triangles are congruent. So remember that we learned the CP-CTC theorem, or not theorem, but understanding. This understanding basically told us that if two figures, specifically triangles, right, because we had this T, which represents triangles, if two triangles are congruent, well then the corresponding parts of those triangles are congruent. Okay, so for triangles, this is known as the corresponding parts of congruent triangles are congruent. That's how we get C, P, C, T, C. That basically just means from one triangle to the next, the corresponding parts, so the exact location of one part, must be congruent and located in the same part of the other triangle. So for example, here we are told that CBA, triangle CBA, is congruent to triangle FED. Well, can we prove that? The CP-CTC theorem, which basically tells us that if these two triangles are in fact congruent to each other, then their corresponding parts must be congruent. So as we can see here, this line segment would match the location of this line segment, and they are in fact congruent. This line segment would match the location of this line segment, therefore they are in fact congruent. This line segment matches to this line segment, and they are congruent. This angle matches the location of this angle on that triangle, and they are congruent. This angle matches the location of this angle, and they are congruent. And this angle matches the location of this angle, and thus they are congruent. Thus, all the parts of these triangles match to the corresponding parts of the other triangle. Thus, those two triangles must be congruent. That's what we get from the CP-CTC understanding. Okay. So let us remember that we learned about different theorems to prove congruence of triangles. And we know that if two things or two figures are congruent, then their corresponding angles and sides must be congruent. All the sides must be congruent, and all the sides must be congruent in order for two figures to be congruent. So triangles can be proven congruent by using one of the following theorems. We have our side angle side theorem, our angle angle side theorem, our angle side angle theorem, our side 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 theorem, and then our hypotenuse leg theorem. Each of which we could use to prove that we have congruent triangles. So here's an example. We are told that ACB and FDE are congruent. And what is the way that we can prove this? Well, we know that they are congruent, which we saw here. But we can use any of the following theorems to prove that congruence. For example, if I wanted to use my angle angle side theorem, I must prove that two angles are congruent. Any two angles are congruent. And I also must prove that a non-included side is congruent. which I saw before. If these two are congruent, then all their corresponding parts are congruent. So I can choose any two angles. For example, I'll use F, A, D, and C. So I have two angles which are congruent. And then their non-included side must be congruent. And as you can see here, my symbols kind of got moved. But if I wanted to see, I can go ahead and show you what it would look like. So let's say when we were given this information, it appeared like this, okay? So now I need to prove that a non-included side is congruent, so it would have to be a non-included side. I can say that I want to use the non-included side BC. So is BC congruent to DE? It does in fact look like that, so I can use this theorem, the AAS theorem, or the angle side theorem, to prove that these triangles are congruent. In fact, I can use any of these different theorems. I couldn't use the HL theorem in this case just because I don't have a right triangle. I can only use the HL theorem, the hypotenuse leg theorem, if I have a right triangle. But any of these other ones, given that all my parts are corresponding to each other and congruent to each other, like we see here, well then we could use any of these theorems to prove congruence as well. So let's use the CP-CTC theorem to prove that these are congruent to each other. These figures are congruent to each other. So how can you justify this? Well, we saw that we have different ways to justify it. And I'll go ahead and just write these down and transfer them over so that we don't forget what we have here. Okay, let me transfer those over. Okay, so what can we use to justify that FC and EE are congruent to each other? Well, we could technically use many of these different theorems, but as you can see here, we are only told congruence about two sides and one angle. So thus we can eliminate some. We aren't told anything about our third angle, so we can take away our SSS theorem. We aren't told anything about two angles, so we can take away these. Only told our congruence of one angle, and so we're left with our side angle side theorem and our HL theorem. Our side angle side theorem says that we have to have two congruent sides and a congruent included angle. We do have two congruent sides, which we see here. We see this side is congruent to this side is congruent to this side. But the included angle of those two sides would have to be A, and we're not told anything about A and D being congruent to each other. So thus we're left with our last type of theorem, and that is our hypotenuse leg theorem. Remember, to prove triangle congruence using the hypotenuse leg theorem, we must first have both triangles be right triangles. And then the hypotenuse of both of our triangles must be congruent. And one leg of both of our triangles must be congruent. So let's see if we meet that criteria. Do we have two right triangles? Well, yes, we are in fact told that both of our triangles are right because they contain one 90-degree angle. So we can mark that one off. Our hypotenuse is congruent. Well, let's locate our hypotenuses. Our hypotenuse is the side opposite our right triangle, usually in our placement. So this would be our hypotenuse, and this would be our hypotenuse. So are our hypotenuses congruent to each other? Well, as you can see here, indicated by the symbol, they are in fact congruent. And then is one leg congruent to each other? Well, let's identify our legs. Here we have a leg, here we have a leg, here we have a leg, and here we have a leg. And as we can see, one of those legs are congruent to each other. This leg is congruent to this leg on the other triangle. So therefore, we can prove in that way that our two triangles are congruent to each other And because we know that our two triangles are congruent to each other, we know that all the angles and all the sides must be congruent to each other. Thus, we are able to prove that our line segment FC is congruent to our line segment DE. Why is that? Well, because once we can prove congruence of those two triangles, well, then we can prove that all of the corresponding angles are congruent to each other and all of the corresponding sides are congruent to each other. Okay, so we've used the HL theorem to prove or to justify that. Let's look at another example. Here we said using congruence theorem, using any congruence theorem, which congruence theorem can be used to prove that BDA and BDC are congruent to each other? So here are our congruence theorems, and we want to prove that these two triangles are congruent to each other. Well, let's see which theorems we can use. Okay. Are we told anything about the angles in this instance? No, we don't see any indication of congruence in angles, so we can eliminate every theorem that needs an angle to prove congruence. So you see here we have an A, cross it out. Here we have two A's, cross it out. Here we have two A's, cross it out. So now we're left with these two. Are we told that we have a right triangle? Do we see a symbol indicated here that indicates right triangles? We do not. So therefore, we wouldn't want to use the hypotenuse leg theorem because we aren't told directly that BDA and BDC are right triangles. So thus, we're left with the SSS theorem. So let's just make sure that we can use the side theorem to prove congruence. Here we see that BD is congruent to BA. We see that CD is congruent to DA. And we see that BD and BD are the same for both triangles. Thus, we can assume congruence because they are the same side, so they are the same length. Thus, they are congruent from one triangle to the next. Thus, we can use the side theorem to prove congruence about these two triangles, that BDA and BDC are congruent to each other. Let's look at another example. Again, we're asked which theorem can be used to prove that WXZ and YZX are congruent to each other. So, in this instance, are we told anything about the sides? Well, not exactly. We may be able to assume congruence here because we do have the same side, right? Actually, I'm going to go ahead and just use one symbol just so we don't get confused. So we can assume congruence there because it is in fact the same side. But we aren't told anything about all the sides, so we can't use side theorem. Are we told anything about how we're told that we have two right triangles, so we might be able to use the hypotenuse leg theorem. But are we told anything about congruence of the hypotenuses? So this would be our hypotenuse, and this would be hypotenuse. Well, we're not told that there's a congruence between that, so we wouldn't be able to satisfy or assume the congruence between those two sides. So I wouldn't use this one. How about, are we told anything about two sides? No, we can only assume things about one side, and that is our side XZ. But we're not told anything about the other sides, so I wouldn't be able to prove congruence of two sides. Okay. So now I'm left with my angle-side theorem and my angle-side-angle theorem. Okay, what did my angle-side theorem tell me? It told me I have to have two congruent angles and then a congruent non-included angle. While my angle-side-angle theorem told me I have to have two congruent angles again and then a congruent included angle. So let's see, included side, non-included side, and included side. So let's see if I can prove this using either of these theorems. So do I have two angles which are congruent? Well, here I have this angle is congruent to this angle, and this angle is congruent to this angle. So I'm able to satisfy that criteria for both of those theorems. And as far as sides go, I can only assume congruence of one side. But is that side an included side or a non-included side? Well, my included side for both of those angles would actually be this side right here. And I'm not told anything about the congruence of my included angle. Thus, I can assume, or I can justify, that I wouldn't be able to prove that my included side is congruent, so I wouldn't be able to use this theorem. But can I prove that a non-included side is congruent? Well, as I see here, WZ, or ZW, is in fact a non-included side, which I see here is congruent. So therefore I can meet that criteria, and thus I can use the angle side theorem to prove congruence. Okay? So those are just some examples of problems that we might see on our Unit 5 exam. And most of the problems when it comes to these congruence theorems are just asking which congruence theorem can be used to prove congruence. And thus you would have to look through each theorem, see what you can prove given the figure or the diagram, and eliminate different theorems until you can isolate the theorem that would best be used to prove congruence. Okay, so what did we go over today? Well, we learned that triangles can be proven congruent using each of our different theorems: the SAS theorem, the AAS theorem, the ASA theorem, the hypotenuse-leg theorem, or HL theorem, and the SSS theorem, right? We are also told that the CP-CTC idea can be used to find the name corresponding parts of congruent triangles. So basically it said if we are told that two triangles are congruent, well then their corresponding parts must be congruent. The corresponding angles in the exact location and the corresponding sides in the exact location. I have also included here a table which indicates which criteria must be met for each of our different theorems. So for the side angle side theorem, we need to prove that any two sides are congruent and then the included angle is congruent. For the angle side theorem, we need to prove that any two angles are congruent and the non-included side. For our angle side angle theorem, we must prove that any two angles are congruent, and then our included side. For the side theorem, we must prove that all three sides are congruent. And for the hypotenuse leg theorem, we must prove that we have so this is supposed to say, oh yeah, that's right. Hypotenuse leg theorem, we must prove that we have right triangles, so each triangle must have a right angle. And we must prove the hypotenuse of that triangle and a leg are congruent to each other. You may be asking, how am I supposed to remember this table? Well, a way you can do it is here. Let's look at the side angle side theorem. We have a side and a side. We have two S's. So because we have two S's, we know that we have to have two sides which are congruent, right? But how do I remember if I need an included angle or a non-included angle to be congruent? Well, as you can see here, S is in between my two congruent sides, my S and S. Thus, it is between my two sides, thus being an included angle, right? Because if I had a triangle and I had two sides which were congruent, okay, then my included angle must also be congruent in order for me to use the side angle side theorem. So basically what I'm getting at is that by this SAS, I am directly being told that I need two sides to be congruent and then an included angle, an angle that is in between those two sides. Whereas in my other theorems, such as my angle side theorem, I'm being told that I need two congruent angles and then a non-included side. And how do I know that side needs to be non-included? Well, because as you can see here, it's not located in between those two angles. It is non-included, not in between those two angles. Thus, it would have to look something like this. Say I knew that this side and this side were congruent to another triangle. Well, then a non-included side, a side not in between those two angles, would have to be congruent. So I could have this side or I could have this side. Okay, So I know that I need a non-included side because my S isn't in between my two A's. Where in this instance, I have two A's, so I must have two congruent angles and an included side. And I know it's an included side because I have my S in the middle. So it's in between those two angles. Those two angles exist outside of that side. So in this instance, let's see. Oops, I'm doing the wrong thing, but I will rewrite that. If I wanted to move this over, so if I determine that the same two angles are congruent to each other, then I would need my included side, so this side would have to be congruent to my other angle. So it had to be included, and I know it's included because my S is in between. Okay? And then side, 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 very simple to remember. One side, two sides, three sides, all those sides must be congruent. And then hypotenuse, leg, the hypotenuse must be congruent, and then the leg must be congruent. Okay? So that's just one way to remember it. But here's a table that shows you which criteria needs to be met in order to use that theorem to prove that two triangles are congruent. Okay? Any questions? Okay. Here are glossary terms, many of which we've seen before, but today we did look at or learn about what a hypotenuse was and what a leg was. Okay, and just a brief review for those of us who are still unsure. We have a hypotenuse every time we have a right triangle, and the hypotenuse is always located opposite of that right angle. So thus, this would be my hypotenuse. And then my legs would be my other sides, my sides which aren't my hypotenuse. And so that's what it would look like in a right triangle. Okay, any questions? Pretty straightforward. Okay, so what is next? What is to do? So tomorrow is an asynchronous day, so you'll be working on independent practice. There are 2 independent practices due. The reason being is that 5.3 is a very short independent practice as well as 5.4. So I believe you can do both in a day, which is tomorrow. But if you need extra time, just reach out to me and I will allow you that extra time to work on this. And then another thing which should be on your to-do list is to study for the Unit 5 exam, which will be on Friday. And more specifically, I recommend to study the review guide. The review guide is always the easiest way to score a really high grade on that exam, as it contains a shortened version of all your PowerPoints and notes, and it contains review problems, which are very similar to the ones you would see on your Unit 5 exam. And we'll take that exam during our class time on Friday. And then on Wednesday, we'll go ahead and do a review day to give you time to study or ask me any questions that you still have. But basically, the gist is tomorrow, please go ahead and work on these practices and then get started on reviewing for your Unit 5 exam. Okay? If you have any additional questions or concerns, you can go ahead and reach out to me at my email, which I'll put right here. And I look forward to seeing you on Wednesday. Bye, guys.